Fellow members, I come back again. We are dealing with the chemicals of life, and our first chemical, we are going to expand water. We're going to expand water and see how water fits into being called a chemical of life. What is water? How do we define water? How do we define water? It would be a hard one to get a definition for water, but let's take it as a chemical, that water is a substance because now we are talking about chemicals of life. Water is a substance consisting of what does it consist of? Consisting of two hydrogen atoms, consists of two hydrogen atoms and one oxygen atom. How are these bonded? Bonded together via hydrogen, not via hydrogen bonds, bonded together via covalent bonds in a fashion, shall I call it a fashion of where this is our oxygen and this is our hydrogen. Two hydrogen atoms bonded to oxygen via this. These will now be called covalent bonds. Those will be called covalent bonds, this and that. So hydrogen shares one electron with oxygen. Each hydrogen shares one electron with oxygen to form such bonds. So this shape water takes up, we shall call it water takes up a V shape. So the water molecule chemically in 3 dimensions, it is V-shaped. That would be water. That would be water. We return to little sandy sea. And say, now, abnormal behavior of water abnormal behavior of water. Water, we have said, has a molecular formula of H2O. So it has 2 hydrogen atoms and 1 oxygen atom. So meaning molecular weight of water would be 2 times 1 for hydrogen, plus 16 times 1, just 1 here. This would give us 18 grams. So 1 water molecule therefore weighs 18 grams. If you consider its counterpart, a hydride of group 6, if we considered hydrogen sulfide, gas, it is even a gas, which has H2S. Sulfur and oxygen are in the same group. But look at this. This weighs 34 grams. That is the molecular weight for hydrogen sulfide. So this behavior here, what do we expect? What do we expect from this? Water having 18 grams and hydrogen sulfide having almost twice as heavier as water. But we find that water is a liquid at room temperature. Hydrogen sulfide is a gas at room temperature. That is defying our rule that the force of attraction between particles is directly proportional to the weight of the substances in contact. So when water molecules are in contact with each other, the force of attraction between water molecules and water molecules themselves would be less than this. But we find that water behaves far different from its molecular weight. What its molecular weight would say. If you have to consider one more substance, let's say ammonia. Even it is ammonia gas, it is NH3. And this would mean it is 14 plus 3 times 1. This is equivalent to 17 grams. We would expect that ammonia and water would be having the same behavior altogether. Almost equal, because the molecular weights are what? Equal. So the question is, what gives water the power to behave abnormally from what we would expect from first principles of chemistry? What gives the water the special attribute? That's our main focus in this. We go ahead even and say, why does water behave abnormally? Why does water behave abnormally? Why? Why is it a liquid at room temperature and its counterparts in the same group are gases at room temperature? So this is what we say here. that water contains oxygen atom. It contains one. This oxygen atom is more electronegative than the hydrogen atoms. Remember, they are bonded to each other covalently, so it is more electronegative than hydrogen atoms. What does this take us? This takes us here that it polarizes. It polarizes the covalent bonds. It polarizes the covalent bonds, creating a partial positive charge on hydrogen we'll call them hydrogens, and a partial negative charge on oxygen. A partial negative charge on oxygen, leading to formation of special bonds between two adjacent water molecules called hydrogen bonds. So water takes us that far. So it means the power of water comes from this, that in one water molecule which has been polarized, partial positive, partial negative, this is partial positive, this is partial negative. So the water molecule is polarized like that. We already said that it has a V shape. If there is an adjacent water molecule here, which has the same shape, partial positive, partial negative, hydrogen bonds start getting formed. This is what we would call the hydrogen bond. That is a hydrogen bond. So the hydrogen bond is formed. This hydrogen bonds are a bit electrostatic bonds. They are formed between two adjacent atoms, but which are not directly bonded together, but they must be polarized. A partial negative charge bonding to hydrogen with a partial positive charge. Other atoms also are more electronegative than hydrogen, so that can happen. So let's see, how does water look like? We want even to call it a water lattice. How does water look like? We are still expanding. Why does water behave abnormally? So I've said one water molecule can be found surrounded by various water molecules. Let's say 4 water molecules are found linked together by hydrogen bonds. So this is partial negative, partial positive, partial negative, partial positive, partial negative, partial positive, partial negative, partial negative, positive, partial negative, partial positive, and partial positive. So how will they be linked? We find that this can link up with that partial negative. This can link up with this partial positive. This partial positive also can link up here. This can find when it has linked up with the partial positive. This partial positive can be found linked up here, and this partial negative can be found